Okay, today we're going to continue on with our discussion of finding different types of areas. And the next thing we need to look at is something we've mentioned a couple of times. These are composite shapes. Okay, we actually mentioned composite shapes a little bit when we were going through the circle unit. A composite shape was finding the segment of a circle. Okay, so we treated it as one shape missing a different shape. Well, that's an example of composite shapes. We also mentioned them the other day, but today we're going to take a real close look at them. We're getting toward the end of the area information for this unit. There's a couple of little things that we kind of need to refresh our memories on, some things we did back in the fall, but this is likely the last day that we're going to dedicate towards doing different area calculations, which means that sometime next week in our 4-day week to finish up the 6 weeks, we're probably going to have another test, probably be Wednesday or Thursday. Okay, so look at it like good news or bad news. Good news is you get another test grade on to the 6 weeks. So for those of you that are in need of some extra grade help, well, you got a big one coming before the 6 weeks is over with. Okay, all right. So today, area of composite shapes. Okay, now obviously sometimes we have to find the area of figures that are not the typical type of shapes that we recognize. Okay, the trick, if you even want to call it a trick, is to redefine what the shape is. Okay, especially if we don't have any language for the shape. We want to figure out a different way to describe it so that we can comprehend what type of a shape it is. For example, if you look at this hexagon that's up there, well, it's not a typical hexagon that we're used to. It's not a regular hexagon. It's just a six-sided polygon. But aside from the word hexagon, we don't have a formula that goes with this thing. And besides the word hexagon, we don't even have any language really to describe it other than it's a concave hexagon, but there's no formula. So what we're looking at today is kind of a method of thinking, and there's two particular schools of thought that we'll discuss. First, and what a lot of people will tend to do, is they will try to find a way to break shapes apart. Okay, when we have a composite shape that we don't recognize, we'll try to find a way to split it apart into shapes that we are familiar with. Okay, and by familiar with, what I mean is we're trying to break it apart into shapes that we do have formulas for. Okay, so this composite hexagon that was up there, it's possible that it could be split into a rectangle and a square. These are shapes that we're familiar with. These are shapes that we have formulas for. So if we can figure out those shapes and those formulas, then one way of treating a composite shape is to split it apart, figure out the areas of the shapes that you now have, and add them up. Okay, that's one method of looking at composite shapes. Now, this isn't the only way that this could have been split apart. For example, some people would look at that composite shape, and like I did here, they would see the long, tall rectangle on the left and a little square on the right. Some people would see it as a square sitting up top and a long rectangle going horizontally underneath. Either way, it's all good. Some people might even see it as three small squares sitting kind of adjacent to each other, one on top and then two down underneath. Okay, and the good thing about composite shapes is none of those strategies, none of those visions are incorrect. Okay, they all work depending on if you have the measurements to be able to work with them that way. And we'll look at it more of it here in just a second. Okay. Now, second school of thought is some people will tend to think of a composite shape as a big figure that is missing something. Okay, so instead of breaking it down into smaller pieces, they think of it as a big piece that's lost a little piece. And that's something, another legitimate way of thinking about it. Again, some people, instead of seeing it as a rectangle and a square, or maybe three little squares, maybe see a big square missing a smaller one. And once again, that is perfectly fine. That is an accurate way of viewing it. But once again, it'll depend upon the particular person looking at it. Some people will see it one way, some people will see it another. The good news is we don't all have to do it the same. Okay? Any way that we see it As long as we haven't done anything goofy, okay, we will all get to the same answers as long as we're following along. Okay, so we could find the area of each of these figures and then subtract one away from the other. Now, as you'll see, it's going to largely depend on how the problems are set up. In some problems like this case, some people will see it as little shapes added together. Some people will see it as various size shapes subtracted from each other. Okay, and that's the way it'll go. But some of the shapes you'll see are very, very clearly a bigger shape that's missing something, or a collection of smaller shapes. Okay, so it just kind of depends on the way the problem's set up. Okay, well, let's have a look at this composite shape. Same shape we've been looking at for the last couple of screens. Let's slap some numbers on it. And then I want you to kind of think to yourself how you particularly see this shape. Different people's brains are going to see it in different ways. I'm curious how people see it. I'll ask you about it here in just a second. Go ahead and copy it down, then we'll work through it. Okay, just out of curiosity, how many people see this shape the first way that I diagrammed it, where it's a long, skinny rectangle on the left side and a little square tagged onto it on the right? Just show of hands. How many people see it that way? Okay, about a third of the class. How many people kind of view it as a long horizontal rectangle on the bottom and a square stacked on the top of it? Nobody sees it that way? Okay, so everybody else sees it as a gigantic square missing a little square? Okay, so I mean, okay, so it doesn't matter how we see it, since the majority of the class seems to see it as a big square missing a little square, then we'll work it that way as well. Now, the first strategy I want you to do is obviously to define it in your own mind. Okay, you have to be able basically to verbalize what it is. So if I ask you, okay, what do you see in that diagram? It sounds like everybody would be saying, I see a big square missing a little square. Okay, so if that's the way you see it, then that's the way you see it. That's kind of the first step. You need to be able to identify or verbalize that for yourself. And the second thing is I want you to diagram it. Okay, I want you to actually on your paper draw big square minus little square. Okay, however you see it, whether it's two shapes being added together or a shape being subtracted from another shape, draw that on the paper. Okay, the next thing we're going to do is we're going to go, okay, I've got two different shapes with a subtraction problem in between them. Okay, and I need to know the areas of these new shapes that I have now defined. Okay, well, if you see it as a big square, that's fine. Big square has a formula. Okay, how do you find the area of a square? Yeah, length times height, or since it's a square, side squared. Okay, so we're going to have side squared on the left. There's that subtraction problem in the middle. Okay, and how do you find the area of the little square on the right? Yeah, it has a side squared. Okay. Now, we also need to transfer the information from the original composite diagram to our new, smaller diagrams that we came up with. Okay, well, what measurements do we know? Do we know the measurements of the big square? Okay, what are the dimensions of the big square? 4 and 4, pretty easy to see. It's marked in the picture actually in several different ways. How about the little square on the right? What are its dimensions? 2 and 2. Okay, so do you have enough information to proceed with going into the formulas and solving this thing? Yeah. Okay, so side squared of the figure on the left, obviously the sides are 4. From that, we will subtract on the right, the sides are 2, and we'll fill that in. Okay. 4 squared on the left, 16. From that, we will take away 2 squared on the right, 4. 16 minus 4 is 12. And then whatever the units of measurement are, inches, centimeters, kilometers, whatever, okay, they will be squared. And no matter whether you see this as a square minus a square, or a little square sitting on top of a rectangle, or a little square sitting next to a rectangle, or 3 little squares that are sitting side by side, we will all end up with the same measurement of 12 square units. Okay, let's look at another. Technically, the shape is a pentagon, but it's certainly not a regular pentagon. Okay, so we couldn't use the formula for the area of a regular polygon on it. Okay, but let's see if we can define this thing. Who's got a definition? A rectangle? Okay, obviously not an entire rectangle, but a rectangle missing a triangle, right? Yeah, so could we write a formula that says rectangle minus triangle? Okay, yeah, we could do that. Okay, anybody have a different way of seeing it? Okay. Now, Isaac's idea is to basically take a big shape and remove a little shape in order to arrive at this thing. Is it possible that you could build it? Like say, okay, I've got a rectangle over there on the right side. Yeah, and I've got a rectangle sitting there on the top left, and then a little triangle underneath it. Is it possible to do this? Of course. Okay. You're basically, when it comes to composite shapes, the only thing that limits you is your own imagination, and then what type of information is provided by the figure. Okay, but I think Isaac's suggestion is probably the best one. We do have pretty clearly a rectangle around the perimeter of that thing. Okay, but from that, we have a triangle missing across that bottom corner. Okay, so that seems like a pretty decent place to start. All right, now if we have a rectangle, okay, that's fine. Do we have the area of a rectangle? How do you find the area of a rectangle? Yeah. Yeah, base times height, just the generic formula. How about the triangle? That's right, 1/2 times base times height. Okay, let's transfer the information from the original composite figure into our new little diagrams and see if we have everything that we need in order to be able to solve it. Do we have the overall dimensions of our rectangle? Yeah, we got 8 and we've got 5. Pretty easy. Okay, how about the dimensions for the base and the height of the triangle? Yeah, okay, and I think we're on to it. Okay, that little guy right there is 3. Can you see why it's 3? Yeah, look at the other side of the rectangle. If the opposite side of the rectangle is 5, then that means the left side of the rectangle is 5 also. You've got 2 units on this little vertical piece up here on the left side, so there must be 3 units missing for the this side of this triangle. Same thing on the bottom side. Okay, you've got 8 units across the top of the rectangle, which means there's 8 units across the bottom of the rectangle. 4 of them are over here on the right side of the bottom, which means there's 4 missing right there. Okay, so our dimensions were pretty easy to find. Now all we need to do is plug into the formulas. 8 times 5 minus 1/2 times 3 times 4. Okay, yeah. Pretty clear. 40. 3 times 4 is 12. Half of that, 6. Yeah, 34 to be a little better. Okay. Instead one thing, and now I'm writing another 34. And then whatever the units of measure are, gummy bears, candy canes, whatever they are, squared. Okay, let's look at another one. Some shapes can be a little bit harder to define, particularly depending on sometimes how the information is situated inside of the diagrams. Because sometimes it's a little difficult to imagine where the boundaries, if you're adding 2 shapes together in order to get one shape, hard to imagine sometimes where the boundaries might be. Okay, well, have a look at this thing. What do we think this might be? Can anybody describe it? Okay, we have suggestions that it might be a rectangle. Okay, it's possible we might have a rectangle there missing 1, 2, 3 triangles around it. Could be defined that way. Absolutely, it could. Anybody come up with a little bit less complicated way or a little bit more straightforward way of getting to it? Okay, some people are suggesting trapezoid. Let's see if we can figure out where a trapezoid might be. Okay, trapezoid will need to have at least one set of opposite sides parallel. Okay, where might we have that? Yeah, If it is a trapezoid, I can't see anything in the picture that would verify it for us. Okay, so I would be scared of treating it like a trapezoid until we had something else going on. Now, we might be able to build something like a trapezoid trying to say, well, I could say like this side is going to be parallel to that side. But now we've got a little bit of an issue. I mean, we could, okay, so all right, I'll cut the trapezoid across there. But now how do we get this top side to make contact so that we can have it? So I'm not sure a trapezoid would be the best way to go about it. Yeah, aside from my malfunctioning board with that little ridge right through there, can you see two triangles? Okay, and again, they're sitting right there in front of us, but sometimes it's just a little hard to imagine that it's there. Okay, now the one thing I'd like you to add to the diagram, I've saved this on there twice, and for some reason the program keeps dropping it. Okay, I wanted those two little guys up top, I wanted those to be congruent. Okay, all right, but if we look at it like that, okay, pretty clear to see that we've got two triangles that are sharing a side, and together they are forming this quadrilateral, whatever it may be. Okay, so let's have a look at the two different triangles and see if we can figure out what's going on with them. Okay, so this time we're building as far as putting two shapes together rather than tearing a little shape away from a bigger one. Okay, let's see what measurements we have. Okay, what do you know about these two shapes measurement-wise? Okay, well, we know the formulas, right? 1/2 base height, 1/2 base height. Okay, have any measurements that we can apply? This guy over here on the right, we got all kinds of stuff on him. We got the 5 and the 13 attached there. Anything else you know automatically about that one? Okay, yeah, we got the 12. And keep an eye on this information that's on the outside. Sometimes when diagrams get a little cluttered or a little complicated, they will have a habit of kind of installing information around the perimeter of the diagram, but then marking off a certain length for the diagram, like the 11 and the 12 are in this case. Okay, so we have the 5 and the 12 and the 13 going on over there. How about any information for this triangle on the left? You got a 12? Yeah, if this guy is 12, okay, coming across the top of that triangle that's on the bottom, well then obviously that side is shared, okay? It's the same information in the diagram. Okay, now there's one more piece of information that's going to be critical to working these problems. Actually, two more pieces, but there's one more in the picture that we haven't found yet. There is a 6 in this picture. Where is it? Yeah, it is the height of this guy. It's a 6. How do you know it's a 6? Yeah, there we go. Okay, we just didn't spot it right off the bat. This 5 is over there, and if the entire length of that guy is 11, then there's 6 units missing right there. Okay. Now, pretty clear over here on the left side, 1/2 times base times height. That 6 is an altitude of that triangle, and an altitude is going to be perpendicular to its base, so we have the base and the height of the triangle over on the left, so 1/2 times 6 times 12. Now, over there on the right side, okay, we all know the formula for the area of a triangle is 1/2 times base times height, but what's the one main property about a base and a height? Yeah, they've got to be perpendicular to each other. Okay, look into the picture. Do we have anything that verifies for us that those are perpendicular? I don't see anything. Okay, but we do have all 3 side measurements of the triangle over on the right. Okay, if you have all 3 side measurements, do you have a way of judging whether they form a right triangle or not? Okay, you do, and you need to know this. Pythagorean Theorem is capable of making the determination, is the triangle a right triangle or is it not a right triangle? And you have to know all 3 sides. So the question is, does 5 squared plus 12 squared actually equal 13 squared? Because if it does, then the triangle's a right triangle. If it doesn't, then it's acute or obtuse, depending on which direction the theorem is unbalanced towards. So let's have a look. 25, 144, 169, and 169 equals 169. The question is that true? Yeah, obviously that's true. It means that in between the 5 and the 12, there is a right angle. That's a right angle. Guys, I mean, it seems kind of trivial, but that's very, very important. If you don't plug in the actual base and the actual height into the triangle formula, it'll give you an answer. It just won't be a right answer. Okay, so it's important to verify that. So now we can actually say, yes, it is 1/2 times 5 times 12. Okay. Over here on the left, you got 6 times 12. What's that? 72, and half of 72, 36, plus 5 times 12, 60, half of 60, 30. Yep, 36 and 30 is 66, whatever the units are, squared. Now, if you chase down Isaac's wave, saw the big rectangle wrapped around the outside, subtract the 3 little triangles, yeah, you'd end up with the same information either way. That's the way composite shapes work. Different people see it in different ways. Let's look at one more. All right, now as you can probably imagine, composite shapes can get as ugly or as creative as the imagination of the person that's putting them together. Okay, so it just depends. We could work composite shapes, you know, all day for the rest of the year and still never cover all of the possibilities. Okay, so let's see if we can't figure out a way to verbalize what this thing is. Isaac says he's got 5 different shapes back there. What do you see, Isaac? Okay, Isaac says he sees a square. I don't see a square. Where's a square? This guy? Right in here? That's not a square. Why is that not a square? Yeah, differing tick marks on the side. So not a square, but Isaac sees a rectangle in there. He also sees 2 triangles, which would be triangle 1, triangle 2. He sees a trapezoid, and then he says he sees a pentagon. Oh, a hexagon. Okay. Now, there is at least a good chunk of a hexagon wrapped around this shape. Okay, but what we need to make a decision about is if you are going to build the composite shape by adding up little shapes, then you're probably going to end up ignoring the big shape. Okay, so if you want to go the route of the 2 triangles on the left and right side and the trapezoid up top, okay, then you probably do not need the rectangle, and you definitely don't need the hexagon. Okay, anybody see it differently? Yeah. A hexagon missing a rectangle. Okay, you know, that'd be a way to look at it as well. Okay, we've been spending a little bit of time here lately looking at regular polygons, so I'm going to stick with that one. Okay, got a hexagon, and from that hexagon, we are missing a rectangle. Okay, but if you like Isaac's trapezoid plus 2 triangles, you can certainly get it that way as well. Okay, how do you find the area of a regular polygon? Yep. Yep. 1/2 times the apothem times the perimeter. Some of you went a little gung-ho yesterday on the quiz, trying to use that formula for every shape you saw. Okay, not a good plan. Okay, area of a rectangle. How do you find that? Yep, base times height. Now let's see what measurements we have from the picture. Okay, pretty clear. Got that 6 tagged onto the side of our hexagon. Okay, what else can we use here? All right, one thing we need to notice is the tick marks. Okay, tick marks are handing us another piece of information that we're not applying yet. Yeah, the top of the rectangle. Okay, top of the rectangle is provided to us by the tick marks. Okay. Now there's another piece of information in there that doesn't seem to be directly connected to what's going on, but we have information about the radius Okay, what do you know about the radius? Radius is going to be 6. That might be important. So I'm going to at least put me a radius inside of our hexagon. And even if they didn't provide that for us, okay, we probably could have figured that one out. Because remember, that's one of the shapes that we talked about. When you look at a regular hexagon is built out of 6 regular triangles. That means if you got a side length of your hexagon is 6, that also means that all of your radii are 6. So because you have those regular triangles. Okay, now let's see what we can figure out from there. Okay, one of the things we're going to need to know is the apothem for this guy. There's the apothem. And we've got, we know we have a side length of 6 going on inside of there. Seems like we're probably going to have to step aside and do a little Pythagorean theorem to figure out what's going on with the apothem on the regular hexagon. So let's go ahead and do that. Okay. A squared plus b squared equals c squared. Okay, what kind of information do we have? Yeah, let's get the hypotenuse in place first because we don't want to miss that one. And then we've got a 3. Okay, yeah, so let's figure out what's going on here. 9 plus b squared equals 36. Subtract the 9 to the other side. B squared equals 27. Yeah, and you take the square root of both sides. 27 is 3 times 3 times 3. There's a pair of 3's in there and an extra 3. Okay, so that technically is our apothem. Okay, so I'll switch variables here. Quit calling it B and I'll call it A, since that's what we typically use for apothem. Okay. All right. Now, it seems like we've got enough information, at least on this side, and perimeter of our hexagon is 36, right? 6 sides, 6 units each side. Okay. Now, from that, we get to subtract the rectangle. Okay. We're still missing a measurement on our rectangle. Okay, so let's see if we can figure out a way to come up with that. Okay, we've spotted how we're going to do it. Okay, if we come back to the original figure looking for information about this rectangle, sure would be nice if we had that measurement. It is needed for the calculation of the area. Now from there, if we build a right triangle, kind of going over to the vertex of the hexagon, we've got a 6 right there. Okay, obviously we're looking for this guy. Okay, so what now? Well, we know that this entire length there is 6, okay? And we know that the overall length, or the overall diameter is 12, okay? Well, 6 of that 12 is used up coming across the top of the rectangle. That leaves 6 units unaccounted for, okay? And as it was pointed out, that would put 3 of them there, 3 of them there, and we have our triangle. Okay, notice anything about this triangle? It's the same as the triangle inside of the hexagon, isn't it? Okay, you've got 6 on your hypotenuse, you got a 3 on your leg. You've got exactly this Pythagorean theorem calculation that we've already done going on, and we've already figured out this measurement. So this height is 3 root 3. Okay, well, this is looking pretty ugly. Let's see what happens. Base times height, 6 times 3 root 3. Okay, well, let's see if we can't put this mess together. When it comes down to multiplication and division, regular numbers are looking for regular numbers and radicals are looking for other radicals. So here in the calculation of the hexagon, what do we have? We have 3 times 36. Okay, those are both regular numbers. Anybody know what that is offhand? 108, okay? 108, and half of that would be 54, okay? Square root of 3 didn't have anybody to combine with, so there it sits, okay? 1/2 was a regular number, the whole number 3 was a regular number, and the 36 was a regular number. They all combined to make 54, pardon me. Yeah. Over here, obviously, 6 times the whole number 3 is 18, and the radical 3 is looking for other radicals. Okay, and it didn't find any. Yeah. Yeah, now we have a subtraction problem that basically says you've got 54 square roots of 3, take away 18 square roots of 3. So how many square roots of 3 are there? There are 36 square roots of 3, and whatever the units are squared. Okay. Now, of course, if we were messing around with this type of a problem on tax, which seems pretty unlikely, I doubt they'll go into anything this in depth, but we would take 36 root 3 to our calculator, punch it in, and get a decimal point for it. And actually, we could have gotten the decimal point all the way back here at the apothem. Okay, but that would have been our answer. And again, we could spend a whole lot of time looking at composite shapes, but it's infinite. Okay, there's an infinite number of different ways of cramming shapes together, or removing one shape for another shape, or two shapes from another shape. Okay, so we've got to get a little practice on our own. We got to figure out how this is going to work. So we got some practice problems. Let's get to it.